this means differentiate. And since we have functions that are mixing x and y, we can't get it into the usual form that we're used to, which is y equals some function of x. Either way, you would have been implicitly differentiating. Let's say that we differentiate this here. We've ended up with treating it like it was an x, so the y would go to 1. And then you would add a dy dx because it's implicit. And then you differentiate the function of x. And then this would be your standard format, dy by dx equals. So that's how it works. So that's how we know we're doing this. This is going to be implicit because we can't get that y on its own. This comes with its own knowledge, needs and stuff. So whenever we've got an x, then it's fine. It just goes ahead as usual. So that will become 1. And then when we have a y squared, and I'm doing this in a strange order because they're probably the easiest ones to do in this order. When we have the y squared, we treat it as if it was an x. So it would become 2x. And then it wasn't an x. We have therefore a y. And because it wasn't an x, we have to add dy by dx. Then the term at the end, 21, let's leave a bit of space here. Going to go to 0 because all numbers go to 0. And this is the hardest one to be thinking about, is product rule. So product rule requires us just to use a little bit of our head, or we could do the method in full. So let's take xy and we'll say u equals x, v equals y, and we'll differentiate both. But then because we are differentiating with respect to x, but it's a y, it's going to become 1 dy dx. So there's the difference there. The product rule says if we've got it in this format, we're just going to multiply it in this way. So firstly we'll have y plus x dy dx. There is a way of doing the product rule in your head. You just hold one to be the same, like as it was before, multiplied by the derivative of the other, and you hold the other one to be the same, multiplied by the derivative of the first one, and then you add them together. The difficulty here, the reason why it's best to do it with your method, is because you have implicit differentiation and you have differentiating y with respect to x. Requires a little bit of extra thought. So that's going to now go up into our question. So plus y plus x dy dx, and for the sake of this I'll get rid of all of that. Now we don't have dy dx. This was the focus up here, right? Was find dy dx, and it's actually here, isn't it? It's there and there. So if we can factorize and get them together, so my plan would be to move across this term here and this term here, although we don't like it becoming negative, just what it is. We'll end up with 2y dy dx plus x dy dx, and then those two terms I've decided to move over will just change their sign. So -1 negative y, in no particular order. I think usually we see the numbers first, and then we'll factorize the dy dx out of these two terms. So we have this, and I'm sure it's a wrap in everyone's head at this point, but dy dx we get rid of the 2y plus x as a whole thing by division on both sides. Probably time to add a bracket around what's there on the right already. And it looks pretty nasty, but it's the answer. You can't deny it. We have dy by dx. And if you want to find the gradient here, you're going to need an x and a y, so a coordinate, because it requires two inputs there. So it seems strange if you're only used to the basic, but there you go.